Alright, hello General Chemistry 1 students. You guys are awesome. Today we're going to go over some theories in chemistry that apply quantum mechanics to better understand how molecules form, or well, how atoms bond together. And well, those three theories are valence bond theory, VSEPR theory, and molecular orbital theory. Now I'll quickly get into valence bond theory and VSEPR theory, mainly to better describe molecular orbital theory. Valence bond theory is essentially this. Those atomic orbitals, like 1s, 2s, 2p, those orbitals will overlap, and like each atom will have atomic orbitals that overlap. And when those atomic orbitals on each atom overlap, well, those atomic orbitals will not disappear. That's the key to valence bond theory. Those atomic orbitals remain. But in the area of overlap between bonded atoms, that is where your bonding electrons will be localized. Therefore, to basically show it as a nice little diagram, let's take hydrogen and fluorine. Hydrogen, which has 1 valence electron, and fluorine, which has 7 valence electrons, therefore needing one more to reach that octet. In the top case, where we were taking 2 atoms of hydrogen and bonding them, well, according to valence bond theory, those atoms will approach each other and their bonding electrons will become localized between each atom, forming a bond. Same thing for hydrogen and fluorine, where the valence electron on hydrogen and one of the valence electrons on fluorine, as the 2 atoms approach each other, those 2 electrons will become localized between both atoms, thus forming a bond. And well, fluorine difluoride, essentially each fluorine atom will approach each other and 1 electron from each fluorine will become localized or contained in an area between both fluorine atoms, thus forming a bond between the 2 fluorines. Now to represent it in more pictorially, essentially, let's look at the orbitals themselves, where hydrogen has the 1s orbital available for bonding, and fluorine has one of its 2p orbitals available for bonding. Well, in the case of hydrogen, as those hydrogen atoms come closer together, those s orbitals will overlap, and the area of overlap is where you will see those bonding electrons. In the case of hydrogen fluoride or hydrofluoric acid, depending on the state of the molecule, HF, hydrogen has its 1s orbital available for bonding, and fluorine has one of its 2p orbitals available for bonding. And that 1s orbital will overlap with part of the 2p orbital on fluorine to essentially give an area of overlap where those bonding electrons will become localized. And in the case of fluorine, well, each fluorine has a 2p atomic orbital that can come together and overlap in between both fluorine molecules to essentially have an area of overlap where those bonding electrons will be. Alright, cool. Now, in valence bond theory, there is a situation called hybridization. This is where the central atom is bound to more than one molecule. Essentially, it states that the central atom will need to hybridize its atomic orbitals in such a way that it can satisfactorily bind or overlap with the atomic orbitals of the bonded outer atoms. Now, the central atom essentially has its s orbital, its 3p orbitals, and its 5d orbitals that it can overlap in some way to allow it to bond to other atoms. And, well, to determine the level of hybridization is pretty simple. The number of atoms that a central atom is bound to is the number of its atomic orbitals it will need to hybridize. So, if the central atom is bound to two atoms, well then the central atom will need to hybridize its s orbital and one of its p orbitals, so 2 atomic orbitals, and that hybridization is called sp. Now in the case of an atom bound to 3 different atoms, well, the central atom will need to hybridize 3 of its atomic orbitals, so its s orbital and its first 2 p orbitals, forming sp2 hybridization. In the case of an atom binding to 4 different atoms, well then it will need the central atom will need its s orbital and all 3 of its p orbitals to hybridize into 4 different hybrid orbitals, each hybrid orbital classified as sp3 because it formed from the hybridization of an s orbital and 3 p orbitals. Or take a molecule like a phosphorus pentachloride. Phosphorus is bound, like that central atom can be bound to 5 outer atoms. Well, that means that the central atom will need 5 of its atomic orbitals to hybridize to form 5 different hybrid orbitals. Well, in the case of an atom bound to 4 different atoms, it's going to form sp3 dehybridization. Essentially, that will be hybrid orbitals that were formed through the hybridization of that central atom's s, each of its p, and one of its d atomic orbitals. And in the case of an atom that is bound to 6 different atoms, that central atom will need to form sp3d2 hybridization, effectively hybridizing its s, each of its p, and 2 of its d atomic orbitals. VSEPR theory is another theory that goes hand in hand with valence bond theory, which essentially lets us predict the shape a molecule will take. And the shape, based off of VSEPR theory, or valence shell electron repulsion theory, is in some way based off of the Lewis dot structures. The key is that the domains of electrons, or the outer atoms and any lone pair located on the central atom, they will repel each other in such a way until those repulsions are minimized. And, well, let's just see some examples of that. Let's take beryllium chloride. So beryllium bound to 2 chlorine atoms, and beryllium has no lone pairs on it. Well, according to valence bond theory, because beryllium is bound to 2 outer atoms, it will need to hybridize one of its s orbitals and one of its p orbitals to form 2 different sp hybrid orbitals. Therefore, the picture on the left shows those 2 different sp hybrid orbitals overlapping with a 3p orbital from the chlorines. And according to valence bond theory again, those bonding electrons will be located in the area of overlap between a 3p orbital in chlorine and one of the sp hybrid orbitals in beryllium. Now, according to VSEPR theory, effectively we have 2 chlorine atoms. They got a lot of negative charge on them thanks to those lone pairs on the chlorines. They are going to want to repel each other as far apart as possible. Therefore, as shown in the image on the right, they're going to form a linear molecule where those chlorines are essentially completely 180 degrees away from each other. Now, let's do another example. And in this case, the central atom is actually going to be boron. So, not beryllium. There we go. Quick fix. Let's take boron trifluorine. Well, boron has no lone pairs on it, and it's bound to 3 different fluorines. Well, since boron is bound to 3 outer atoms, it's going to need to form sp2 hybridization, or 3 different hybrid orbitals that are classified as sp2 because they were formed from boron's s orbital hybridizing with 2 of its p orbitals. Well, that can be shown in the image on the left, where boron has 3 of its sp3 hybrid orbitals overlapping with a 2p orbital on each fluorine. And again, according to valence bond theory, those atomic orbitals, they do not disappear, and the regions of overlap between the orbitals in fluorine and orbitals in boron is where you will see your bonding electrons localized. Now, according to VSEPR theory, you're going to form a trigonal planar molecule, or essentially those fluorines are going to repel each other as far apart as possible until you have essentially 100 degrees of separation between each fluorine. Now, for this class, I don't expect you to remember to know the names of the different molecular shapes, and I'm not going to expect you to really draw molecules based off of valence bond theory. That's not the point. I want you to understand molecular orbital theory. But one more example of valence bond theory and VSEPR theory, because it is expected that you guys at least get introduced to this material during Gen Chem 1. Let's look at methane, or CH4. Methane, we have carbon bound to 4 hydrogen, therefore the hybridization on carbon is going to require one of its s orbital and all 3 of its p orbitals, because in order to form 4 hybrid orbitals, you need to hybridize 4 atomic orbitals. Therefore, the hybridization classification of each hybrid orbital on carbon is going to be sp3. Therefore, those sp3 hybrid orbitals on carbon are going to overlap partially with the 1s orbitals on each hydrogen. And where they overlap is where you will see their bonding electrons localized. And those hydrogen are going to repel each other as far apart as possible until each essentially is 109.5 degrees away from each other. Now, in the case of a molecule like ammonia, NH3, it's kind of similar to methane, where there are 4 domains, but one of those domains is actually a lone pair on the central nitrogen, instead of nitrogen being bound to 4 different atoms. Therefore, since nitrogen is bound to 3 atoms, the level of hybridization is going to be sp2, because it needs to form 3 hybrid orbitals, which requires 3 atomic orbitals, or its s orbital and 2 of its p orbitals. Therefore, ammonia, or NH3, is going to have a hybridization level of sp2. Now here's the thing, where that lone pair on the nitrogen, even though each hydrogen will have some repulsion from each other, the lone pair on the nitrogen is going to repel those bonding electrons between hydrogen and nitrogen greater than the repulsion of each hydrogen atom. Therefore, instead of having that tetrahedral shape from 4 domains as seen in the example on the left, you're going to have a trigonal pyramidal shape. Essentially, that lone pair on the nitrogen is going to squeeze those hydrogens somewhat closer together, not giving a perfect 109.5 degrees of separation. But again, this is just visualizing valence bond theory and VSEPR theory at work. Here's what I actually expect you guys to be able to utilize for the upcoming exam, which is molecular orbital theory. Now, valence bond theory basically stated that those atomic orbitals, they remain when atoms bond to each other. They do not disappear. Molecular orbital theory actually says that atomic orbitals disappear, and instead molecular orbitals are then formed. And therefore, according to molecular orbital theory, bonding electrons do not necessarily have to be localized between bonded atoms, because those atomic orbitals are no longer present. There's no region of overlap. Instead, those bonding electrons are going to be under the influence of the entire molecule. And for molecular orbital theory, we can calculate something called bond order. This is essentially understanding what kind of bond is between the atoms in that molecule, like single, double, triple bond, or bonds that are kind of in between. A little strange according to Lewis dot structures, but it makes sense according to molecular orbital theory. Now, here's the thing. For our class, we're only going to focus on diatomic molecules, molecules that consist of two atoms, because molecular orbital theory is much easier to explain in those situations. For molecular orbital theory, we represent that through molecular orbital diagrams, which is essentially taking those atomic orbitals on the atoms that are bound together and having them disappear to form molecular orbitals. And those are represented by the orbitals that molecular orbitals are shown in the center of the diagram. Now, whenever you see a molecular orbital, if it does not have an asterisk to it, that is a bonding orbital, and the electrons in that orbital will be bonding electrons. Now, if a molecular orbital has an asterisk or a star, that is called an anti-bonding orbital. Therefore, electrons that go to fill that anti-bonding orbital will be known as anti-bonding electrons. In the case of dihydrogen, here's how we would fill those molecular orbitals. Well, each hydrogen has with it one valence electron, and just like subshells, just like atomic orbitals, molecular orbitals will only accept 2 electrons each. Therefore, let's say we take one valence electron from one of these 1s orbitals on one hydrogen, we can move it to the bonding orbital, and with the electron from the other atom, it's essentially going to get a spin flip and be used to completely fill that bonding orbital. I want to make clear that when you are filling molecular orbitals, you start from the bottom up. You start from the bottom and then you work your way up. In this case, we only had 2 valence electrons to work with, so they both went to fill the lower bonding orbital. Now, to calculate the bond order for this molecule of dihydrogen, or 2 hydrogens bound together, it's going to be the bonding electrons. In this case, the bonding orbital has 2 electrons. And we are going to subtract the anti-bonding electrons, of which there is 0 because the sigma star, or the molecular orbital up top, it has no electrons in it. So that value is 0. And then we are going to divide that total number by 2. Therefore, 2 minus 0 is 2. 2 divided by 2 is 1. Therefore, we would say that this molecule has a bond order of 1, which basically means we would expect to see a single bond between a molecule of dihydrogen, which is what we do see, even according to the Lewis dot structure. So, cool. Now let's take a hypothetical situation of 2 helium atoms coming together to bind together. Well, each helium atom, helium is in the first period, which means it only has the 1s orbital, atomic orbital available to it. And when those atomic orbitals disappear to form molecular orbitals, we are going to have a sigma bonding orbital and a sigma star anti-bonding orbital. Now let's start taking our atomic orbital electrons and using them to fill our molecular orbitals. Well, each atom or each helium is going to give an electron to fill the sigma bonding orbital. And now that there are 2 electrons already in that orbital, we will work up toward the anti-bonding orbital. And well, we still have 2 electrons left over. Therefore, we can use those guys to completely fill the sigma anti-bonding orbital. In this situation, we have 2 bonding electrons from the sigma bonding orbital, and we have two anti-bonding electrons from the non-bonding, from the sigma non-bonding or anti-bonding orbital. Therefore, 2 minus 2 is 0, divided by 2 is going to be, well, 0. That means that we have a bond order of 0 if we were to take two atoms of helium and bind them together. Now, having a bond order of 0 basically means you're not going to have a molecule. And that makes sense because helium, it's a noble gas. Its outer shell of electrons are already filled. It does not really have any encouragement to form molecules with other elements, including itself. Or another way of saying this, according to molecular orbital theory, we have just as many bonding molecular orbitals filled as we have anti-bonding molecular orbitals. Therefore, there's really no encouragement to bind. Now, let's take a more complex situation, like something in the second row of the periodic table. That's where we have the p block elements. These things will have more complex molecular orbital diagrams. Now, for an exam, I will essentially give you this skeleton of the molecular orbital diagram, where essentially I have the atomic orbitals from each atom and then the molecular orbitals that are formed. I will only expect you to know how to fill the atomic orbitals and then how to fill the molecular orbitals. And, well, here's how we'll do it. Again, with fluorine, its 2s orbitals are completely filled. So those atomic orbitals are going to be completely filled. And for the 2p orbitals, well, since fluorine is 5 elements into the p block, it is going to have a total of 5 electrons in its 2p orbitals. And, well, technically I should fill each p orbital once and then start filling in and start doubling up. Well, I'm just going to cheat a bit just for the sake of time. So, let's say we take those guys and we just duplicate them and put them over to the other set of 2p orbitals from the other fluorine atom. Now, here's how we can start filling up the molecular orbitals. Well, we'll take one electron from each s orbital to start filling up that lowest bonding orbital. And we still have 2 valence electrons left over, so we can fill the anti-bonding orbital. Alright, cool. Now, for the overlap of 2p orbitals, we're going to see sigma bonding and sigma anti-bonding orbitals, but also we're going to see 2 sets of pi bonding orbitals and 2 sets of pi star bonding orbitals. Now, 2 sets of pi star anti-bonding orbitals. Just like before, we're going to start filling up bottom and then working our way up. So the sigma bonding orbital, it can take 2 electrons, and that's what we're going to do. 2 of those sweet, awesome electrons. Now, for the going one step up for these two individual pi molecular orbitals, think of it back to when we were filling up the 2p orbitals. We would fill up each first once before we would double up. And we're going to do that again for molecular orbitals that are on the same level. So effectively, let's take an electron from each fluorine atom to fill up those 2 different pi bonding molecular orbitals. And then we can start doubling up electrons to completely fill up those molecular orbitals. Alright, cool. Those pi bonding orbitals are now completely filled. Now we can start working on those anti-bonding pi orbitals, or those pi star orbitals. Well, we're going to need to take an electron from each fluorine to fill each non-bonding pi star orbital first. And then if we still have electrons left over, we can start filling up one of those pi star orbitals, and there's one remaining electron left over. That remaining electron, essentially, it's going to gain a spin flip to become like so. All right, we essentially took the 7 valence electrons from each fluorine, so a total of 14 electrons, and we use those to fill the molecular orbitals like so. Now let's count out the bond order. Well, the amount of bonding electrons would be 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 bonding electrons. Now for the sigma star and the pi star orbitals, those would be anti-bonding electrons. So counting those up, we have 1, 2, 3, 4, 5, 6. So we have 8 bonding electrons and 6 non-bonding electrons. 8 minus 6 is going to give us a value of 2. 2 divided by 2 is going to be 1. Therefore, our bond order is 1. So what would we expect to be the bond between 2 fluorine atoms? Well, a molecule of 2 fluorine atoms would have a single bond, or a bond order of 1. Hey, cool. That makes sense. Now, once again, I want you to know, I would give you the skeleton of the molecular orbital diagram. You guys would need to know how to fill the atomic orbitals on the outside and then fill the molecular orbitals. In this case, let's look at that molecule of hydrogen and fluorine bound together. Well, effectively, that 1s orbital on the hydrogen is going to be at an energy level that's actually too far away for it to overlap and form a molecular orbital with fluorine's 2s orbital. So effectively, those electrons in fluorine's 2s orbital are gonna form what's called a non-bonding orbital. It's not bonding, it's not anti-bonding, it's just non-bonding. So it doesn't really have an effect in our bond order calculation. These are effectively going to be like the lone pairs, one of the lone pairs on the fluorine atom. Now, for the case of hydrogen and fluorine, we have those 3 different p orbitals, but we only have a single s orbital. Whenever you overlap orbitals, however many atomic orbitals you use to make molecular orbitals, it will make the same amount of molecular orbitals. So I only have 1 orbital here on hydrogen, and therefore it can only combine with a single orbital on fluorine. Therefore, 2 atomic orbitals, we're going to get 2 molecular orbitals, which are the sigma and sigma star molecular orbitals. What's going to happen is that those other 2p orbitals for fluorine, they're just going to form non-bonding orbitals, or effectively those lone pairs on the fluorine atom. They don't have anything to do with the bonding. Now, let's start filling those molecular orbitals first. So the sigma bonding orbital is going to take an electron from both atoms. Cool. Now I still have 4 electrons left over from fluorine. Well, those are going to be used to fill the non-bonding orbitals, or the 2p orbitals that did not participate in forming molecular orbitals. And well, just like before, fill each orbital first before you start doubling up. So now I can start doubling up with the remaining electrons, and this last electron, it's going to get a spin flip, so I'll just take 1 from down here. And then boom, we have the 1 valence electron and the 7 valence electrons. So the 1 valence electron from hydrogen and the 7 valence electrons from fluorine accounted for to essentially have this 2s orbital not participating in bonding, and then 2 of the 2p orbitals on fluorine not participating in bonding, they're going to become the lone pairs on the fluorine atom. What is important is that we do have a bonding orbital that has electrons in it. Therefore, we can calculate a bond order. Again, bond order, it takes into account the bonding and then the non-bonding molecular orbitals. So we're going to ignore the non-bonding orbitals, or the 2s and the 2b orbitals, and we're going to take these two electrons in the sigma bonding orbital. So 2 electrons, and the sigma star anti-bonding orbital has no electrons in it, so that's going to be 0. So 2 minus 0 is going to then be divided by 2 to get the bond order. Or, well, 2 minus 0 is 2, 2 divided by 2 is 1. We have a bond order of 1. So what would we expect between a molecule consisting of hydrogen bonded to fluorine? Well, a single bond. That's what the bond order of 1 represents. And that is what we do see. Now, here's the last example I'm going to show you. This is again combining atoms from the P block in the second period of the second row of the periodic table. This is going to be dinitrogen, so 2 atoms of nitrogen. Well, effectively, we're going to effectively form those 2s orbitals are going to form sigma and sigma star bonding and anti-bonding molecular orbitals, and then the 2p orbitals from each nitrogen are going to form a sigma and sigma star orbital, and then 2 sets of pi orbitals and 2 sets of anti-bonding pi star orbitals. Well, let's just take our valence electrons and see how they work into the system. Well, I can fill my lowest bonding orbital, my sigma bonding orbital, and then I can start working on filling my sigma star orbital. Now I have essentially 1, 2, 3, 4, 5, 6 electrons to use to fill up my molecular orbitals. So let's work on that. 1 electron will go to fill the lowest sigma bonding orbital, and one of the electrons on nitrogen is going to get a spin flip and be used to fill the remaining spot on this sigma bonding orbital. Now we still have 4 electrons left over. We are going to fill each bonding pi orbital once first. We're going to fill each with 1 electron first. And now we are going to start spin flipping our remaining electrons to fully fill the remaining spot on each bonding pi orbital. Now, there we go. Nitrogen, it's from group 15, therefore it has 5 valence electrons. Therefore we have a total of 10 electrons to work with, and the atomic orbitals were based off of the period numbers, so this is a good way of showing where the group number and the period number is starting to come into play when it comes to forming molecules, and I think that is so awesome. But anyways, 5 valence electrons from each nitrogen gives us 10 electrons to work with. Well, we use those electrons to completely fill the lowest sigma and sigma star orbitals, and then to fill the sigma bonding orbital and then each pi bonding orbital that were formed through the combination of 2p atomic orbitals. Or let's determine our bond order for a molecule of 2 nitrogen atoms bound together. Well, we have, as far as bonding electrons go, well, we have this sigma bonding electron we have 2 electrons down here in the lowest sigma bonding orbital, but we also have a sigma bonding orbital and 2 pi bonding orbitals. Therefore, counting up the electrons we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 bonding electrons. We have 8 bonding electrons. And now we have, as far as anti-bonding electrons, well, the only anti-bonding orbital that is filled is the lowest sigma star orbital. And the number of electrons that are in that orbital are 2. We don't have any electrons in the above on any of the remaining anti-bonding pi star orbitals or the highest anti-bonding sigma star molecular orbital. Therefore, we don't have any additional anti-bonding electrons to take into account. Therefore, our equation is 8 minus 2 divided by 2, which that's just going to equal, well, 8 minus 2 is 6. 6 divided by 2 is 3. Therefore, what does a bond order of 3 mean? Well, that means that we would expect to see a molecule of dinitrogen to have a triple bond as what is joining those 2 nitrogen atoms. So each nitrogen atom would have a triple bond. And, well, yeah, that is in fact what we do see in reality. So, cool. That is how you form molecular orbital diagrams to represent the formation of molecular orbitals from the original atomic orbitals. So this week, for extra credit, which will be due the end of day Saturday, April 4th, I want you to fill the molecular orbital diagram for NO, nitrogen bound to oxygen. And that's actually going to be on the next slide. So I want you to fill the molecular orbital diagram for that guy and then calculate the bond order for that molecule. So add up the bonding electrons, subtract the non-bonding electrons, then divide that difference by 2. And as always, if you get the entire extra credit right, plus 2 points. If it's mostly right, plus 1. So the actual diagram, not only do I have the skeleton made for you, I've already oriented the valence electrons for you guys. So literally, I just want you, for this extra credit, show me how the valence electrons from the atomic orbitals are used to fill the molecular orbitals in the center, and then calculate the bond order. You will notice that in the case of nitrogen, where we had dinitrogen, we had all these bonding orbitals filled and none of these additional anti-bonding orbitals. Well, we have one more electron, so you're going to see that go into one of these pi star orbitals. So you're not going to get a nice neat number of 1, 2, or 3 for the bond order. You're going to expect to see something between those whole numbers. Yeah, and that's what molecular orbital theory helps us see. That sometimes when a Lewis structure would say that we have like a double bond between something, in theory, it might actually be more similar to somewhere between a double and triple bond or between a single and double bond. And, well, you'll see that when you calculate the bond order for NO. And, well, for the rest of the semester, here's the general guideline. Next Monday, you'll get access to your exam 3 and then the practice exam. And, well, for that exam, you're not going to really see valence bond theory or VSEPR theory. That's more appropriate to just show with a picture. Molecular orbital theory is where we can actually have a problem where you fill a molecular orbital diagram. No, anyways, whew boy. Honestly guys, you guys are the last lesson I do every week, just like it was in the regular semester. So, man, I am glad to be done with lessons this week. Anywho, you guys were fun face to face, and I enjoy reading the quality work you guys give me when you submit stuff to Blackboard Learn. So without further ado, at the 40-minute mark, enjoy your weekend, guys. You are awesome.